Hello, and welcome to my research profile presentation today on the topic of low latency wireless, theoretical foundations, and experimental experience. I first want to introduce myself. My name is James Gross. I'm an associate professor here at KTH since 2013. And in general, I'm working on and interested on wireless networking. So in particular, I'm focusing on a couple of different research fields: resource allocation for cellular networks, for example. I'm also interested in machine-to-machine communications. I'm interested further on theoretical network performance models, in particular on network calculus. And then we're also doing some work on simulations and experimental prototyping. Now today, I want to dive into our research with respect to low latency wireless communications, in particular for critical control applications. And the motivation from this comes from a new type of application classes in contrast to what is going on in today's networks in terms of application classes that are present. So if you consider the situation in today's networks, you're seeing broadly we have two application classes. We have, on the one hand, applications where humans are interacting with humans, and on the other hand, we have applications where humans are interacting with computers, so the typical client-server service model. And this is a historical development. The first application class was there before the second, and going from the first to the second, we see a massive increase in efficiency and also a massive increase in devices and in traffic that we're witnessing today in networks. However, and this is important, it's always humans which are still directly involved in the communication loop. And what we're witnessing today is that this is now about to change. So for already a couple of years, we're now talking about so-called machine-type applications, where we have a certain state in reality, and we deploy sensors which are measuring this state. And these sensors are then pushing this information back through a wireless access network to some server. So this is a typical monitoring or metering application case that a lot of people have been looking into with respect to machine-type applications. Network operators are interested in this. And the research community has been also focusing on this in terms of, on the one hand, energy efficiency, and on the other hand, network scalability. However, this is only part of the story. And a much more powerful application case comes out of closing the loop. Okay, so having actually the server over here, then feeding back some information depending on the state information that it gets from reality, such that actuators can then influence the state in reality in a beneficial way. Now looking at that closely, that's of course nothing else than closed loop control. It's a very powerful and wide application class. However, it comes with a quite distinctive set of requirements, and these requirements are completely new to communication networks, and in particular completely new to wireless access networks. And just to give you a flavor of these requirements, typically we see that low latencies need to be provided by the networks in comparison with high reliability levels. Okay, so typically for different application scenarios, you see them here. For example, if you look at industrial production, and in that case, factory automation in particular, we're seeing deadlines that need to be met within a few milliseconds, whereas the reliability level of the data communication needs to be extremely high, so in the range of 10 to the power of -7, and lower packet error rates that are required. And the open question that the research community is facing today is actually how to design efficient systems for such requirements. And in my research, I'm addressing these topics. I want to first cover some theoretical foundations, and then we're coming more to some practical work. So when we're starting to address these systems from a theoretical point of view, we witness a problem with respect to the performance models that we have. So if you look, for example, at ergodic capacity models like the Shannon capacity model, then they're always resting on an infinite time horizon with respect to decoding the information. That is fine for, let's say, modeling networks with a sufficient amount of resources and also with longer delay requirements, but as the delay requirements are getting shorter and shorter, this is getting a problem. And so we have to look for new performance models that we can actually employ. And there is a pretty well-known performance model that was developed a couple of years ago at Princeton University, and it considers a so-called block length limited performance, where we're seeing in this formula that we're actually the rate of the system here, R, is given by the Shannon capacity of the system, but then we have a certain cost that comes in addition. And this cost depends on the block length, which is given in this formula by the M, and it depends on a block error probability. And this block error probability comes from the fact that when we're decoding with respect to a finite horizon, then there is an error probability naturally arising that we cannot decode the transmitted information. And the question is now, and this formula to some extent answers this, as the block length limitation gets more and more severe, or as the error probability over here gets lower and lower because we need to communicate more and more reliable, then this cost, this overall cost, gets actually higher. And that's a very interesting performance model to conduct research. So many issues with respect to this block length limited performance of wireless communication systems are not understood today. And in our research, we have been recently looking at the performance of relaying. So in the case of relaying, you certainly know that you have a source over here, and the source is then trying to transmit data here to the destination over a so-called relay. And the problem now with block length limited communication is here that when you want to go over the relay, that of course takes time when you go over the relay instead of the direct transmission. And so you are already facing a block length limitation, a delay limitation, and now you have to halve that time in order to actually first transmit data to the relay and then to the destination. And so intuitively, you would say that should increase the cost that we're witnessing in comparison to ergodic capacity models. However, and this is really interesting, we were able to show that the opposite is actually true. So in this graph, you're seeing here on the x-axis the block length limitation. So you can say this is more or less the delay of the system, the delay that we're trying to reach. And on the y-axis, you're seeing actually the rate of the system. And we're comparing here direct transmission with a relaying system, which are operating at the same Shannon capacity that is given up here, if we're not looking at the block length limitation. And then if you switch to the block length limited performance model, then you can actually see that the cost, in particular for a low delay, is much higher when you do a delay limit and when you do direct link transmission, instead of when you're going over the relay. And this is counterintuitive. And the reason for this is actually that in the case of relaying, the individual links get much better, they're much stronger, and so you can communicate actually at a higher error rate in comparison to the direct link transmission. And this is compensating for for cutting the time into two, or cutting the delay into two halves. And if you're interested in more, in some more research with respect to that, you find more information here in these two publications. I would like to now come to our experimental experience in this area. And here it's fundamental to understand that from a practical point of view, any research that we're doing is typically met with some skepticism. And this skepticism is coming from the fact that whenever you're doing mathematical analysis or simulations, you typically introduce a modeling error. And this modeling error, when you're talking about very low reliability levels, or very high reliability levels, this modeling error is actually too high, okay, to convince practitioners. And so prototyping, experimental research is mandatory in this area. It's really essential. And so when you're then starting to do experimentations in this domain, questions come up like which levels of reliability can be actually met in practice. So where do we end up? We have our theoretical research on the one hand, but what can we actually do in reality? Or how are actually such systems designed? So which design methodologies do you take, or which architectures are actually suitable for so-called low latency wireless communication systems? And we've been addressing all these questions over the last couple of years by developing a novel system that we call the echo ring. So the echo ring, first of all, is a pure protocol overlay that we developed, and it's based on a distributed real-time medium access control scheme, which is essentially realizing in token passing. And in token passing, what you basically do is you transmit a control packet here from node to node, and whenever a node has this control packet, then it can actually transmit, it can actually access the channel. And this is then governing the medium access control. Now what we did on top of that is that we put into the token transmission the instantaneous channel states as they're seen from the individual nodes. And on top of that, we then realized cooperative communication schemes, such that in this graph, whenever this node, for example, is transmitting a payload packet to this destination over here, then this guy knows instantaneously which of the other nodes here in the system, okay, somewhere over here, which of these other nodes are actually the best position to relay, to safeguard kind of like the communication that is going on. And so if the communication then fails over here, then actually one of these guys over here can take over, and that is pulled by the corresponding source. And because the channel state information is very, very accurate, this then leads to a very good system performance. Okay, we have a couple other features in this protocol that we developed. If you're interested in more information, you find actually the more information in these publications down here. One striking thing here is, of course, that we implemented then this protocol on software-defined radio platform, which in this case was the WARP platform from Rice University. And just to show you some experimental results that we achieved. So in this graph, you're seeing actually the packet loss rate for a dedicated node that we're tracking in the system over an increasing number of terminals that are present in the network. And we're comparing here echo ring, that's the blue curve over here, with a set of other curves. So different token passing schemes which are not having cooperative communications employed, and there's also one reference scheme, that's the red guy in here, which is actually Karasen's multiple access. And what you basically get from this graph is that by the means of cooperative communications, when you have enough spatial diversity, you see that the echo ring system actually for 4 and for 5 nodes over here has a packet loss rate of 0. And this is a measurement that has been conducted over a couple of days with respect to a target deadline of 10 milliseconds. And while obviously the other systems are not able to reach that. So we conclude from that that cooperative diversity really brings a significant benefit to so-called low latency wireless communication systems. Another interesting message from this overall research is that it's not easy to break packet error rates in the range of 10 to the power of -5 and below, simply because the quality of your implemented system then also becomes important. And for example, if you have implementation bugs in your code, they tend to show up in your practical measurements. Okay, now I would like to get to reality and show you the system here in this place. This is now a live demonstration of the echo ring system. So we have here in this room a deployment of 4 different nodes, one over there on the table. Then we have 2 transceivers here on this big table and one further one back here in the room. This topology in this room that we showed you is now demonstrated and represented here in this application on this computer. And you see here on the screen, you see now the 4 different boards represented by these dots. And we can now live demonstrate you the dynamic relaying capabilities of echo ring by, for example, clicking on one of these nodes, and then you see that there are certain arcs, and these arcs are dynamically set up depending on which of the nodes is now instantaneously in the best position for relaying a control packet or a payload packet. And this leads to the stability of the system that we showed you also on the last 2 slides. And we can live demonstrate you this now in this application as well, when we have a look at the so-called delay profiles of this system. So here we're showing you the empirical cumulative distribution function of the packet delays in the system. And the system has a target delay of 10 milliseconds represented by this red bar. And essentially you're seeing that none of the packets is actually exceeding this deadline. So we're facing an extremely reliable wireless communication system here in this live demo. So concluding, low latency wireless networking is really currently a topic which is picking up a lot of interest. And that is due to the fact that on the one hand, we have many still open theoretical problems, while on the other hand, this topic really has a high practical relevance, which makes it really interesting and attractive. Now, from our experience so far, we can show that actually from a theoretical perspective, but also from an experimental perspective, cooperative communications is really a key technology, a key approach to realizing these low latencies with ultra high reliabilities. Having said that, when you want to do research in this domain, I believe you need to support or you need to strengthen your research by experimental work, simply because this is mandatory to do credible research in this domain. So thanks for your attention.